Okay, so this is gonna kind of build off of some of the stuff we've been working with before. So like on, I don't know, whatever the last day of the class, Thursday was, we did like the arithmetic series where it was like our arithmetic sequences, so like our lists of numbers, and then when it was series, it was just like summation of that stuff, because summation is just us like adding all those things together. So it's the same concept as that, except for now with geometric. So the difference between the arithmetic and geometric, geometric sequences where we multiply between terms. So like, 2 or times 2 or something like that, whatever. But you're multiplying between terms. And then again, series of that is just taking whatever those values are that are in our sequence and just doing the summation of those. So you got that same summation notation there where the, I is equal to, that's where we start, and then whatever that top one is there, that's where we stop, and then we remember the summation is just adding all that stuff together, and then there's just like an explicit formula that gets plugged into that spot, but very, very similar to the stuff we were working on Thursday. And then the other thing is, you remember on Thursday how there was like special little formulas we could use to do that instead of adding all the stuff out by hand? Same concept here, where this capital S sub whatever just stands for the series going up to whatever that number is. Both of these formulas are the same thing. They just switch around like your 1 and your r to the power of n, and then just kind of do that same thing here, 1 and then your r. This one, they just do the same thing, just flip them around. Both of those will still get you your answer that you need, so either of those is cool to use. Okay, but mostly just plugging into formulas. And G sub 1's first term, r is your constant ratio, how much you're multiplying by each time, and then n, however many terms you're doing it for. Okay, so let's take a look in our packets then, and kind of go through some examples here. So the first one, what they've got is they say rewrite the finite. Finite just means it's stopping at some point. It's the opposite of infinite. Geometric series in sigma notation. So sigma notation is that same summation notation that we were doing before. So if we're writing this in that summation notation, that's when we're going to have kind of that weird E-shaped thing that stands for summation. And then when we write this out, we got to know a handful of things. We got to know what our G sub 1 is, we got to know what our R is, and we got to know what our N is. So we'll start figuring those things out. So like G sub 1 would be our first term. So looking at our stuff in our list here, our G sub 1 or our first term would be 6. R stands for our constant ratio, so that's how much we're multiplying by each time. It gets a little bit tricky here because we've got fractions and stuff, but since these first two aren't fractions, those are the ones that I'm going to use, and I'm thinking, okay, what would I have to multiply 6 by to get 4, which is kind of tricky, but the opposite of multiply is divide, right? So couldn't I work that backwards and basically take those numbers and divide them? So like if I did 6 divided by 4 and just reduce that down, 6 over 4 would be 3 over, I think I wrote that backwards. Other way. I'm going to go 4 over 6. Sorry. So we're working backwards. So if I go 4 over 6, that would reduce down to 2 over 3, right? So if I took 6 times 2/3, isn't 4 2/3 of 6? And then if I took that value times 2/3, we get that gross number. And again, those are kind of gross, but if you always take like your first two and just divide them, because it's the opposite of multiply, that'll give us what we need. So like to go between that one and that one, we'd multiply by 2/3. Same between there and there, multiply by 2/3, same thing keeps going there. So that 2/3 then that we're gaining by each time, that would be our R value or our constant ratio. And then the other thing we need for this is our N, and our N is just our number of terms in the list. So like here we got 1, 2, 3, 4, 5, 6 terms in that list. So that would just be 6 because there's 6 terms listed out there, okay? Then when we plug it into our little formula here, if we want summation notation or sigma notation, the bottom one is always where we're starting. So we're starting at the first term. So it'd be like our I is equal to 1. Our top number here is always the N value that we're ending at. So there was 6 values in our list, so that N is just going to be 6. And then the thing that goes behind it here is kind of like our geometric sequence formula. So that is the one, if you remember, it's always, and I can write it out here, it's always like G sub 1 times R to the power of, I'm going to switch that to I instead of N. I minus 1 because we're using I as our letter there. but you remember that formula we had from geometric? That's just where that's coming from. So like our G sub 1 is 6, times our constant ratio for the R is 2/3, to the power of, and then in our case here, we're just going to leave it as the I minus 1, and then that would just be like your generic formula for that. And again, that's just in that sigma or summation notation. Then the easier way to actually evaluate this or solve it out is to use one of those formulas that we had in our notes. So either this one or this one, doesn't matter which one you use. I think I'm going to use the first one. But if I'm using that formula, so that formula is like S sub n is equal to G sub 1, and then parentheses 1 minus R to the n over 1 minus R. And again, I'm just pulling that from the note sheet. I'm just writing it here so we can make reference to it. And then our values here are just the same as they were before. So like our G sub 1 is still our first term, you know, constant ratio there, and then number of terms. So we can just take those guys and fill them into these spots here. So the capital S stands for our series. So we're trying to find the series up to value n. In our case would be value 6 because there's 6 terms in our list. So it'd be like S sub 6 is equal to, and then we'll just plug in those things there. So our G sub 1 is 6, parentheses 1 minus, our R value is 2/3, to the power of our n value is 6, over 1 minus our R value, which is that 2/3 again. And then I would just kind of work my way through here and kind of solve this. So like here, you're going to kind of get some gross numbers when you work this out, but we can just turn them back to fractions using our calculator. So like if I was trying to do this 2/3 to the 6th out, we could do like 2 divided by 3. We know it's a gross number there. And then if we do that to the power of 6, still a super gross number, but then we can use our cheat button there and use the math and then frac to turn that into a fraction for us, so we're not having to round that number, you know what I mean, to make it a nicer value. So it would be the same as the fraction, 64 over 729. So like it would be like 6 times 1 minus 64 over 729 over, and then we could just do 1 minus 2/3 would be 1/3. We can do that one in our heads. And then really here, we could probably type this up. We probably could have actually typed it all out in one step there. I think I'm going to type this whole top out as one step and then have the bottom as a third there still. So if I do that top out as one step and I leave this fraction in my calculator still, if I go 6 parentheses 1 minus and then go second answer to pull that value, should make me good there. And then again, gross number, but if we go math, frac, can turn it into a fraction for us just so we can write it down. And sometimes they might ask you to, like, you know, show your stuff out with the fractions, so not going to hurt to do it like that. But then we know to get down to like our answer there, we can just take that value and divide it by this value, so we can just keep it in there and divide by 1/3. Or we could have multiplied by 3 because that would be the same as dividing by a third. Again, get our gross number there, math, frac, enter. That gives us 1,330 over 81. And again, that's just a little bit more exact way of doing it instead of rounding each of those little fractions down. But yeah, as long as you're keeping it all in your calculator, you should be able to get to that. And it's like 16 something as an approximate. But mostly just plugging into the formula. Okay, so this one, they give us the stuff in the summation notation already, and then we've got to figure out what that would be. Again, we can do each of these things out, you know, do all 10 of the first terms there and add them all together, or we can just revert back to that same formula, so that's going to be much easier using that formula. So if we can do the same thing where we come up with like our G sub 1, our R, and our N, we should be able to plug into that formula, right? A little bit trickier thing here, though, is they don't give us a list of numbers, but based on this information here, we could come up with our own list of numbers. So to figure out like what our term values would be, you could just plug in like first term, second term, third term, and that kind of thing, and kick out values. So to find like first term, so maybe write that, find first term, plug in 1, because that would be our value for our first term, for the I. That'll kick out the first term. So like if I went there and I did 3 to the first power, wouldn't that just kick me out of 3? So that would mean that, and I'm plugging into that little formula there because that's my like explicit formula of this. So that would mean that my 3 there for my G sub 1, first term is 3. And then to be able to find the rate or the ratio that we're going at, you might want to find a couple of the terms in the list. So like if we did that for like a handful of terms to find our R, if we come up like with a sequence here, so like if we did like find sequence, we'd be like plugging in like 1, 2, 3, and a handful of them for I. That's how we're coming up with those values. So if we do that a few times, so like we know the first one's 3. Next one, if I took a 2 and put that into that spot, it would be like 3 squared, which we know 3 squared is 9, right? So I was like 3 to the first, 3 to the second. Same thing for like the third term. It'd be 3 to the third. 3 to the third is 27. So that's kind of like the beginning of our list of numbers, and it would keep going there. So now that we kind of have a little list of numbers, now we can look at those and go, okay, how much are they increasing by each time? So like we know to get from 3 to 9, be times 3. From 9 to 27, isn't that also times 3? So isn't that probably our constant ratio then of times 3 for that R? So that's what we're going up by. And then n is just however many terms we're doing this for, and it's always the same as whatever this top value is in our summation thing, so that's just 10. So we just know that's 10 then. And then now that we've got that information there, we can take that information, plug it into that same formula we used here. Okay, so if I plug into that same formula from here, it would be in our case S sub 10, because our n there's 10, so S sub 10 is equal to, and then it's always our G sub 1, which is 3, parentheses, 1 minus our R value, which in this case is also 3, to the power of n, so the power of 10, parentheses, over, and then it would be 1 times our R value, and our R value is 3, times 1 minus 3, or divided by 1 minus 3. And then again, I just do some solving out there. So like I said, you can probably just do them all in steps here. So like, 1 minus 3, that'd be negative 2. And then you can do this all in one shot here if you want to. So like if we go 3, parentheses, 1 minus 3 to the power of 10, and close our parentheses, that should pick up order of operations there. Get some big number there, which is fine. So negative 177,144, just so you got some work out there. And then just take that value and divide it by negative 2, and you should end up with 88,572. And again, that formula is a much easier way of doing that than figuring out what the first 10 things in the list are and then adding them all together. Okay, and then just the other couple things on the notes here. So if you're ever dealing with like a percent increase or decrease, just make sure when you do that whatever percentage they give you, you either add or subtract from 100. So like if it's a percent increase of something, don't forget that you're like paying for the whole thing still plus whatever the increase is. And then here, like you could also go the opposite way for decrease. You take your whole value of something, the 100%, and subtract away like what the discount would be or what the decrease would be. Just be kind of careful of that if they give you some questions like that. And I think our next one here might actually deal with that, so that's why that's in there. So if we go to this next one here, example 3, this one's kind of a lot going on. So Earth's population 2009 was about that huge number there and growing at a rate of 1.188% a year. Assume this rate continues. We're supposed to express the population n years after 2009. Okay, so here they're not asking us for the summation of this or the series of this. They just want like the sequence of this. They just want geometric sequence. So behind this, maybe I'll write just geometric sequence, not sum on this. So they don't want us to use the special formula thing. They just want us to set it up as a regular sequence. Okay. So like I was saying before, if this is something that's growing at this rate, we want to use that concept of percent increase. So like really our rate would be the 100% plus this percent here, so like it's like 100% plus that 1.188. So really our percentage is like 101.188 percent, because we're going up, or because we have the full value already, and then we're just going up by that amount. So if you just do it by that decimal amount, you're not taking into account like the current population. It's just growing by that. So that's the value we're actually going to use for our percentage, and our percentage would be like our rate when we plug into our formula. So remembering back to our geometric formula, it's the G sub n is equal to, and then it's always our first term here. So our first term in this case would be that big value there. So 6, 7, 9, 0, 7 zeros there. Big old number. So that'll be our first term. Then our rate would be this value here, and don't forget to turn this into a decimal when we do it. So you remember when we turn something to a decimal, we divide by 100 or go over, 2 spaces there. So we put into our formula, it'd be 1.01, extra one in there, 2 ones, and then an 88 to the power of, and it'll be just to the power of n. Okay, so that's all they want for that one because they just want us to put it into that geometric business, okay? And then we go from there because now they want us to, so suppose in 2009, population used up U billion tons of oil, and then if the population grows at its current rate, so doing this out, the oil usage remains the same per capita, how much total oil will be used in the next 10 years? Basically, you're just taking this U value and you're putting it in as like this value instead, okay? So like instead of us knowing that population, or instead of us knowing that value for that oil, we're just putting that guy instead in there for the U. And again, this one's a little bit confusing, but we're going to do the actual solving out. So I'm going to write it in the summation notation first. So in that summation notation, we're doing this out for 10 years. So 10 will be our top value there, starting at the first year. So we'll put a 1 in there. Then, like I said, we're going to use this same formula, but instead of us giving us that value there, we're going to use that U in there instead. So you're just going to put a U in there as kind of like your first term, parentheses, and then you're just using the same thing we had here. So 1.01188 to the power of n there. And then we would just use that to plug into that formula that we had from our notes. So this would be the same as, again, we don't know what this is, so we're just going to leave it as the U, parentheses, 1 minus, always what our rate is here, so 1.01188 to the power of, we do know our n in this case, because our n is the 10 as that top number, so the power of 10 over, and then it's 1 minus our rate value. And then I don't think that this comes out like super nice fraction-wise, so we might just have to leave it as decimals. So this U here, because we know it's multiply there, we can just ignore that and just solve this part out, then throw it back in at the end. It's just multiply, so we can come up with what this value is, then just throw a U with it. So I would just take that other stuff besides the U and do it out on my calculator. So like, let's go top part first. So 1, actually, let's go parentheses. Parentheses. Actually, did I write that wrong? I did write it wrong. No parentheses there. Parentheses there. So 1 minus 1.01188 to the power of 10. Get that decimal number there, and again, I'm just going to leave that decimal guy on my calculator, divided by, and then this here, so I'm going to put parentheses because I haven't subtracted the 1 yet. So 1 minus 1.01188, parentheses, get that gross number there, so we'll just approximate it here. That's approximately 10.55. We'll just go with that. And again, that'll just be times the U because we don't know what that U value is. And then in part C, they actually tell us what to use for a U value. So then they just say if our U value there for tons of oil or whatever it is 30, then they want us just to figure that out. So you're just taking this formula we came up with here, so that approximately 10.55, putting a 30 in there for the U, and then just seeing what that's approximately equal to. So you could either just leave this number on your calculator times 30, or you could use that one that you approximated there. Either way is cool. But I get that it's approximately 316.56-ish. If you use that number instead, I left it on my calculator, but if you use that number instead, it might be a little bit different than that, but that's cool, and it would be measured in billions, or billion tons. And again, that one's a little bit of a tricky problem there, just the way they phrase stuff's a little bit weird, but that's kind of that one. Okay, and then last one here, they use an example in the book and actually map out the formula for you. Um, so it says, example 4 in this lesson is somewhat unrealistic because if you go back, whatever. So the example 4 in the book, I'll read it to you. It says the maximum number of natural ancestors that you could have is 2 parents, 4 grandparents, and 8 great-grandparents. So they're just talking about, like, not, some random person that you call Grandpa Joe or something like that, just like your true actual biological grandparents, biological great-grandparents, and that kind of thing. So it's only possible to have 2 biological parents, 4 biological grandparents, and then so on there. So it says assuming that no one appears twice, so that would be like kind of like double cousins or double aunts and uncles, where maybe like 2 sisters married 2 brothers in another family or something like that. Then you've got a little bit different there. But assuming that's not happening, they say in the past n generations, you've got S sub n, natural ancestors, where, and this is the important thing for us, we're going to use S sub n is equal to, and they've got 2 plus 4 plus 8 plus, and then it's going to keep going there. And then they've got it as it's always 2 to the power of n, because you got 2 sets of parents or grandparents or whatever, and then it'll just keep, expanding out your family tree. So that's the formula they use for that, and then they also give the other formula there for the S sub n with all the stuff plugged in. They've got it as 2, and then 2 to the power of n minus 1. They switch around the order on that, but again, we can write it either way, and then n minus 1. So that's just the formula that the book comes up with, and they're just using like the constant ratio stuff. So like first term is 2, so like g sub 1 is 2 still, because that's our first term. Our rate would be 2 as well, because each time you're multiplying by 2 there. So that's how they're coming up with that value. And then your n is just however many generations you're supposed to go back here. In our case, so it says how many generations do you need to go back to have 500 natural ancestors, assuming no duplicates. We actually don't know what our n value is. That's what we're trying to find in this case. Okay, so we've got this formula set up here, but we don't know the n. But what we do know is our S sub n there, whatever our n value is going to kick out 500 ancestors. So basically, you're just plugging into that formula, but you just got to solve for n instead of just kicking out a series value. So we'll just put that stuff in there. So like I said, it's already got that stuff in there because the book just had it. Put that 500 in there for the S sub n, so it'd be like 500 is equal to, and then like I said, the book kind of set it up for us for that formula there. And then I just start solving this out. Realistically here, if this is 2 minus 1, or 2 minus 1, isn't that just 1? And if we divide by 1, isn't that just the same as what the top is? So really, if that's just 1 on the bottom, do we even need that there? Not really, right? So I'm just going to get rid of that stuff because it's just 1. So then we're at the point where we got like 2 times, that stuff there. So to get rid of that 2, maybe I'll rewrite this as 5. So I got rid of that because it's just 1. So 500 is equal to 2 times 2 to the power of n minus 1. Then, like I was saying there, the next step I would go with is to get rid of that multiply by 2 by dividing by 2 on each side. Because then that'd be 250 is equal to, those 2's go away, so you just got what's left in parentheses, 2 to the power of n minus 1. And then I'd get rid of the subtract 1 by add 1. So 251 is equal to 2 to the power of n. And then here what kind of sucks is you got to use logarithms, and logarithms is next chapter. But just a refresh on logarithms here. So when you've got power of a variable like that and you're trying to get rid of it, what you do is you do the log of each of these sides. So like you're going to do the log of 2 and the log of that number. And then you get some number there, and then basically whatever number you get, you're just going to divide by that number. So really here what we're going to do is we're going to divide by the log of 2 on each side. And like I said, we're going to do logarithms next chapter as far as we can get through it before the end of the year. But it's kind of annoying when they throw them in like this. But either way, basically you're just going to divide. So we're at the point where it's going to be like the log of 251 divided by the log of 2. And that'll kick out an n value for us. And again, I wouldn't expect you just to know that off the top of your head. And there is a log base 10 button on our calculator that we can use. So there should be a button here next to the 7 that just says log. If you just do log of 251 divided by log of 2, it'll kick out your value there. So it tells us that our n is approximately equal to 7.97. and the n with this great grandparents, whatever thing, is number of generations. So realistically, we can't have like a 7.97 of a generation. So you would just round it up to 8. So it would be about 8 generations. So 8 generations back, you would have 500 natural ancestors, just like parents, grandparents, great-grandparents, great-greats, and so on. But yeah, logarithms. We'll do more of that next chapter. Okay, so you just got that book page for tomorrow then, and then tomorrow we'll get into the 8-6 stuff.